Hello students, let us explain about graph in motion. The first graph I give you is a graph of distance versus time. When you analyze carefully this graph, you see how from 0 to 20 seconds the car is moving faster than in the interval from uh, 30 to 50 seconds. You know why? Because the slope of the line that you have here in the interval from 0 to 20 seconds is greater than the slope of the line that you have in the interval from 30 to 50 seconds. So the slope is equal to the instantaneous velocity in the graph of distance versus time. That is the kind of graph that we have here. So as greater the slope, faster the car is moving in that interval. Now, when we analyze the interval from 20 to 30 seconds, we see, that the line is a horizontal line. So it means that the distance in this case is constant. So basically, the information about the velocity we can get from this graph in this interval is that the velocity there is zero. So the car is at rest in the interval from 20 to 30 seconds. Now, when the graph is going downwards, like in this interval from 50 to 60 seconds, that means that the car is traveling backwards, So the distance uh, from the starting point to the position, the actual position of the car is decreasing. So always, when in a graph of distance versus time, you see this behavior. So a graph going down, it means, that the distance is decreasing, right? So the car is moving backward in that interval. Now, let us analyze the graph of velocity versus time that we obtain, you know, uh, based on this graph of distance versus time. So there is a connection, right? There is a relation between these two graphs, right? So this graph of velocity versus time is obtained based on this graph of distance versus time. So in the graph of velocity versus time, we find that from 0 to 20 seconds there is a constant velocity. So here we have a constant velocity because in this case, the line is horizontal. So the slope of the line here is zero. So from 20 to 30 seconds, the velocity of the car is zero, right? Again, we have a horizontal line, but this line also is on the x-axis of the graph or on the graph of the time, right? So that means, right, that we have no velocity at all here. So the velocity is zero in the interval from 20 to 30 seconds. Now, when you analyze the interval from 30 to 50 seconds, that is over here, again, the velocity is constant, right? And it's lower than the velocity in the interval from 0 to 20 seconds. Why? The height of the line or the distance from this horizontal line in the interval from 0 to 20 respect the time axis, is greater than the distance, of the velocity line here uh, respect the time axis of the graph. So it's evident, that then here the velocity is greater than in this other interval from 30 to 50 seconds. Now in the interval from 50 to 60 seconds, the velocity is negative. And the velocity is negative because remember that in this interval from 50 to 60 seconds in the graph of distance versus time, we had the car going backwards, you know. So we had that the distance was decreasing. So due to that reason, we have a change in the motion, in the direction of the motion. So that's why we have here a negative velocity, So we have a velocity in the opposite direction. Based on this graph of velocity versus time, we then obtain a graph of acceleration versus time. So there is a relation between the graph of velocity versus time and the graph of acceleration versus time. So you can see how when there is a change in the magnitude of the velocity, we have a spike in the graph of acceleration versus time. So you can see how the acceleration from 0 to 20 seconds is 0 because the velocity here is constant. So the acceleration in this graph is 0. At 20 seconds, we have a spike, in velocity and is sorry in acceleration, and it's because the velocity have changed, suddenly from a maximum value here to 0. So this variation in velocity you see here in this graph of velocity versus time is the reason that you have a spike in the graph of acceleration versus time. Since there was a decrease in the magnitude of the velocity, then that's why the acceleration is negative. So we have in this case really a deceleration, or a negative acceleration in the object. Now, at 30 seconds, that we have an increase in velocity in the graph of velocity versus time, we have another spike in the graph of acceleration versus time, right? And then in this case, this acceleration is positive because there was an increase in the magnitude of the velocity. And again, we see a negative acceleration at 50 seconds because there was again a change, or a decrease in the magnitude of the velocity at 50 seconds. So that's why you see here a spike in the graph of acceleration versus time, and this is a negative acceleration or deceleration also because we go from a high value or a positive value of velocity here in this graph of velocity versus time to a negative value of the velocity in the graph of velocity versus time at 50 seconds. So that's why we see a negative acceleration or deceleration in this part. You can see how from 30 to 50 the acceleration is 0 because the graph of velocity in the interval from 30 to 50 is horizontal, and again you see how from 50 to 60 the acceleration is 0 because when you go to the graph of velocity again, you see how the graph of velocity versus time is a horizontal line, so the velocity is constant in these intervals. Now let us analyze what happens when we have a problem of uniform acceleration. So here I show you how look the graph of acceleration versus time in a problem with uniform acceleration. Then when we have a uniform acceleration or a constant acceleration, the graph of acceleration versus time is a horizontal line. So that means, that acceleration is constant, the magnitude of acceleration is not changing, with the time. Now, when you go to the graph of velocity that is related to this graph of acceleration versus time, you see how the graph is a straight line that goes up. So you have a graph, that is an increase in velocity following, on a straight line, okay? Because we have a uniform acceleration, so we have a constant increase in velocity, right? So remember, uh, always this relation between the acceleration and the velocity. And when you go to the graph of distance versus time, you see how this graph is not on a straight line now. And why it's not? Because the uniform acceleration of the car implies, that the distance covered by the car is going to be growing, more and more rapidly with the time. Okay, so that's why we have here that this graph for uniform acceleration, the graph of distance versus time, does not follow a linear relation. So we have a graph that is not a line, that is not a straight line in this case. Now, let us see here what happened, when we have an initial velocity that is different than 0. When we have an initial velocity different than 0, if you want to find the distance that was traveled by the car, you have here two components. You have first this rectangular part that is representing, the distance traveled by a car with constant velocity, with a velocity equals to the initial velocity and with 0 acceleration. This would be this part of the graph, this rectangular part over here. I have divide this graph in two sections, one rectangular section here in the base of the graph and one triangular section here, on the top of the graph. So this rectangular section over here corresponds, to the distance traveled by a car with a velocity v sub 0 and zero acceleration. And then this triangular part that you see here, correspond with the distance that has been traveled by the car due to the acceleration. So the total of both distances give you the total distance that was traveled by the car in the interval of time t. Okay, so remember that in this case, let me make a quick correction here. In my graph, what we have here is, in this case, time, and what we have here is just velocity. So we have a graph of velocity versus time. Now, I want to show you some exercises, right, that are going to help you to understand better this problem. So the first, I give you a graph. This is a graph again of velocity versus time. So we have velocity here, we have time here, and then the first question is, if a car is moving along a straight road, does it ever goes backward? This is just the first question. So the question is, I have a car that is moving around along a straight road, so it's going backward. This car in the interval from 0 to 2 seconds is going backwards. In the interval from 2 to 4 seconds is going backward. In the interval from 4 to 6 seconds, well, the answer is that this car is never going backwards. And why is never going backward? Because regardless that in this part, the velocity is decreasing, the graph of velocity is still above the x-axis, so the velocity is still positive, right? So the car is not going backward. So remember, that we have a car going backward with a graph with negative slope when the graph was a graph of distance versus time. But our graph here is a graph of velocity versus time. So you cannot get confused about that, right? We have here a velocity that is decreasing, but it doesn't mean that the car is going backward. It just means, that we have a deceleration in the car. So this car is never going backwards. Now, they ask you during which interval of time the distance traveled is the greatest. From 2 to 4 seconds is when we have that the distance traveled by the car is the greatest. Why? Remember this. As well, for example, the velocity would be, the instantaneous velocity would be the slope of the line of distance versus time. The distance traveled will be equal to the area under the graph of velocity versus time. So when you analyze the area from 0 to 2 seconds, the area under the graph from 0 to 2 seconds, so the area of this triangle, okay, and you compare this area with the area of this rectangle, right, that we have from 2 to 4 seconds, and you compare that with the area under the graph from 4 to 6 seconds, you see how the greatest area here is the area from 2 to 4 seconds. So this area under the graph, okay, is a measure of the distance that has been traveled by the car. So as greater the area under the graph, greater the distance that was traveled. So that is the reason that that we say that the greatest distance is in the interval from 2 to 4 seconds. In the last part, they ask you at which point, is the magnitude of the acceleration the greatest. So we can say that at point A, so at this point over here, okay, the instantaneous acceleration, has the greatest value. Why? Because the instantaneous acceleration is equal to the slope of the line of velocity versus time. And the slope of the line of velocity versus time have its greatest value in the interval from 0 to 2 seconds, means at point A. because here we have velocity constant, so we have a slope that is 0. Here we have a velocity that is negative, but the negative slope here in magnitude is lower than the magnitude of the slope, independently that this is negative, is this slope is in magnitude is lower than the slope from 0 to 2, right? The slope from 4 to 6 is in magnitude lower, in absolute value lower, than the slope from 0 to 2. So that's why, we can say without any doubt that the acceleration have its greatest value from 0 to 2 seconds. I have here another exercise that I want to share with you. So it's this exercise over here. They give us this graph. It's a graph, of velocity versus time. And then we have here 2 points, 1 point here that correspond with 4 seconds. At 4 seconds, we have a velocity of 4 meters per second. And then we have another section of the graph that is from 4 to 5 seconds. And from 4 to 5 seconds, we have an increase in velocity from 4 to 12 meters per second. So the first question in this case is, what is the average velocity from 0 to 4 seconds? So from 0 to 4 seconds, using this interval over here, we have an increase in velocity from 0 to 4 meters per second. So if we know the velocity is equal to the initial velocity plus acceleration time, and we know that the initial velocity in this graph is equal to 0, right? We can say, that velocity is equal to acceleration time. So the acceleration will be equal to the quotient of the velocity and the time, right? So we have a velocity of 4 meters per second divided by 4 seconds, that is the time of this interval, so you will get 1 meter per second squared. So that would be, in this case, the answer to the problem. So what is the average acceleration from 0 to 4 seconds? The average acceleration from 0 to 4 seconds is 1 meter per second squared, or 1 meter per second per second. So in every second, we have an increase of 1 meter per second in the velocity of the car. Now, they ask you what is the average acceleration from 5. This is from 4 to 5 seconds. There is an arrow here. So this is from 4 to 5 seconds. What is the average acceleration from 4 to 5 seconds? We're going to do exactly the same thing, but now from 4 to 5 seconds, we have that the initial velocity here was 4 meters per second, right? We have an initial velocity different of 0 in this interval. We have an initial velocity of 4 meters per second. So we have, using the same formula, velocity equal the initial velocity plus acceleration time. So as in this case, the initial velocity is different of 0. Remember that in this case, the initial velocity was 0. That's why I just canceled this term. But in this case, the initial velocity is different of 0, right? So what I'm doing now, I'm going to say that the final velocity minus the initial velocity is equal to acceleration time. So the acceleration is equal to the final velocity minus the initial velocity divided by the time. So final velocity here is 12 meters per second minus the initial velocity, that is 4 meters per second, divided by the variation in time in that interval that was 1 second. So that gives you 8 meters per second squared. So your acceleration, in this second interval that go from 4 to 5 seconds, is 8 meters per second squared, or 8 meters per second. So you have an increase of 8 meters per second in velocity in each second. Now they ask you to find what is the average acceleration from 0 to 5 seconds. So from 0 to 5 seconds, we have an initial velocity of 0, a final velocity of 12 meters per second, and then we have a variation in time that go from 0 to 5 seconds. So if I have to find here the average acceleration from 0 to 5 seconds, I'm going to say, that this average acceleration, starting with the same formula, the velocity is equal to initial velocity plus acceleration time, and taking that in this case, when I go from 0 to 5 seconds, the initial velocity is 0, so I have the velocity is equal to acceleration time, so acceleration is velocity over time, So my velocity go from 0 to 12, sorry, from 0 to 12 exactly. So I have 12 meters per second here divided by the time they go from 0 to 5 seconds. So I have 5 seconds here. So when I divide 12 meters per second by 5 seconds, I get 2.4 meters per second square, right? So this is in this case the average acceleration, from 0 to 5 seconds. There is a last question here to say why is the average of the average acceleration from 0 to 4 and from 4 to 5 seconds different that uh, from 4 to 5 seconds, sorry, different that the average acceleration from 0 to 5 seconds. So again, why is the average acceleration from 0 to 4 and from 4 to 5 seconds different than the average acceleration from 0 to 5? So basically what they say is if I find the average, between this acceleration and this one, it would be 4.5 meters per square seconds. So adding and dividing by 2 these values of acceleration. And that value 4.5 meters per square second is different of the value of average acceleration that we found here. So why this happens? Why the average of the average acceleration from 0 to 4 and from 4 to 5 is different than the average acceleration from 0 to 5? It's basically because we cannot calculate the average acceleration from 0 to 5 as the average of the average acceleration from 0 to 4 and from 4 to 5, because the slope of the line, if we find a line from 0 to 5, right, that line, the slope of that line will be different than the slope of the lines, from 0 to 4 and from 4 to 5. So that slope would be greater than the slope of the line from 0 to 4. That slope would be lower than the slope of the line from 4 to 5, right? So we will have here, from 0 to 5, a line with a total different slope, you know, that the line from 0 to 4 and from 4 to 5. And it's going to be a value of a slope that is greater than the slope from 0 to 4 and lower than the slope, from 4 to 5. This is exactly, what we obtain as result, in this case. We get 2.4 that is greater than 1 meters per second square and is lower than 8 meters per second square. So we got as average acceleration from 0 to 5, 2.4 meters per second square. So you have to keep in your mind that if you have to find the average acceleration from 0 to 5 in a problem like this one, you cannot find the average, you cannot find the average between the two accelerations that we have here in the interval from 0 to 4 and from 4 to 5. You cannot do it in that way. So you must find the acceleration for that new interval that go from 0 to 5 seconds. So hopefully, with this video, I will help you, to understand better this section of the book about graphing motion. So I encourage you to read the book, look at the examples out there, solve the exercises and watch all the videos, that I am sharing with you. Thank you for your attention.